It's okay? Can I start? All right. It's not too loud. Somehow it's a bit loud. Now, like this, like this. Okay, so any questions about the exercises? Yeah. 2 over D, yes. Sorry. Any other questions? So I said many things last time, but in principle it can all be summarized very briefly, that we are dealing with a theory which has a bunch of local operators. And as I said, there was sigma, epsilon, there was t mu nu, but there are other operators which I did not name yet. And so as I said, the operators are, so these operators are primary operators. So they satisfy this condition that k mu acting at operator at 0 is equal to 0. And these primary operators, their correlation functions, they satisfy certain constraints following conformal invariance. So these constraints can be written as follows. So if you have a conformal transformation x going to x prime, so it's a conformal transformation, and consequently we have dx prime over dx equals some scale factor omega of x times some orthogonal matrix. Then under any such transformation we must have that O of O1 of x O1 of x1 dot 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 has to be equal to omega of x1 to the power delta 1 times this matrix, which I denoted D, and it's only there if there are indices. If there are no indices for scalars, there is no such matrix, times correlation function O1 of x1 prime dot dot dot. So I wrote such constraints. And so that's where we arrived. So the next step is to understand concrete consequences of these constraints. So by the way, these constraints, of course, is not everything. So you can say that these constraints, sometimes we say that they incorporate conformal kinematics. In this sense, they are analogous to Lorentz invariance and quantum field theory, to Lorentz invariance constraints. So they are nice, they have to be understood, but they are not everything. So by themselves, they would not fix the theory. So there's going to be some extra ingredient, which you can call dynamics, which will be necessary to fix the theory. I have not talked about it yet. But this needs to be understood as well. These constraints, they have a series of important consequences, and let me first tell you what consequences are, and then we will discuss how to derive them. So the first property is that as a consequence of this constraint, the 2-point functions of primary operators, let me write it, say, O1 of x1, O2 of x2, is non-zero only if delta 1 is equal to delta 2. And if this condition is satisfied, then we have O1, so let's say OX1, OX2, as I said, is equal a constant divided by x1 minus x2 to the power 2 delta, but we can set this constant to 1 just as a normalization. By rescaling the fields. I mean, this may look innocuous, but this is actually not absolutely trivial. Because if you just had scale invariance, if you only had scale invariance, but not conformal invariance, then we could have a correlation function O1 x1 O2 x2, which would be proportional to 1 over x1 minus x2 to the power 1 plus delta 2. So scale invariance by itself would not forbid such a correlation function, yet conformal invariance forbids it. So this is not trivial already. Now, if you go to the 3-point function level, then we have the following result, that the 3-point function, oh, by the way, here I'm dealing with scalar operators, but there is an analogous formula for operators with spin. So let me write it down. So with spin, we would have O mu of x1. Well, let me write O mu of x, O mu of 0 is equal to delta mu minus twice x mu x nu divided by x squared divided by x to the power 2 delta. Again, the same property is true, that the 2-point function is non-zero only if the dimensions are the same, and it must have this particular form with this particular linear combination of tensors. Now you see it's even more non-trivial, because if we had just scale invariance, then we could write an arbitrary linear combination with an arbitrary relative coefficient that would be consistent with scale invariance. But conformal invariance says that only this particular linear combination should arise. And if you have more indices here, then the rule is the same. You are only allowed to contract indices of different fields with this matrix, with this particular linear combination. So, for example, let me write down. So let's call this object I mu nu. Then, for example, if I have a correlation function of two stress tensors, T mu nu of x, T mu nu T lambda sigma of 0, then this is going to be equal to some constant times E mu lambda E nu sigma. And now, of course, I have to symmetrize, right? So there's going to be another combination, E mu sigma E nu lambda. And now I have to subtract the traces. So the metric, the tensor, stress tensor is traceless. So I have to subtract from here the trace of this quantity. And so actually this trace is equal to some constant I think it's again 2 over d, but check. Delta mu nu delta lambda sigma. But it's just a trace. Divided by x to the power 2d. 2d because we are dealing with a stress tensor. Oh, sorry, yeah, I mu lambda, exactly. Thank you. So the 2-point functions are completely fixed. The three, yeah, yes. So here was spin 1, here spin 2, and then you go to generalize to arbitrary number of indices. Now the 3-point functions are also fixed, at least the functional form. So let me write down the formula. So let's first for scalars, O1 x1, O2 x2, O3 x3 is equal to some constant divided by so x1, 2 stands for the distance between points x1 and x2. And here I'm going to introduce a number h1 to 3. I'm going to write down what's equal to x13 to the power h132 and x23 to the power h231. At this number hij is equal to delta I plus delta j minus delta k divided by 2. Yeah. So you see, it's so what are the important remarks? Of course, if we just had scale invariance, once again, we would have a much bigger and infinite, in fact, freedom to write down these 3-point functions. Because if we only had scale invariance, then the only condition we had to impose is that h, the sum of these h's, had to be equal to the sum of the scaling dimensions, delta 1 plus delta 2 plus delta 3. And this equation would have infinitely many solutions. And yet, imposing scale invariance, it turns out that from these infinitely many solutions, only one solution survives. Only one solution is consistent with conformal invariance. So that's the first remark. The second remark is that, so as I said, it is customary in conformal field theory to fix normalization of 2-point functions by rescaling the fields so that the 2-point function is 1 here. So once you fix normalization in this way, the coefficient in the 3-point function, you can no longer change it. So it is fixed then. So this we set to 1. And here then we have a certain coefficient, let me call it f123, which is now an observable coefficient. So in every conformal field theory, it makes sense to ask what is the value of this coefficient. So it's you can say it's an analog of a coupling constant in normal quantum field theory, except that in quantum field theory you can vary the coupling constant, while here in the conformal field theory it's going to be fixed. So there's going to be some, for any 3 operators, there's going to be one number. And in fact, jumping a bit ahead, it will turn out that if you know in the conformal field theory the dimensions of all operators, so if you know all scaling dimensions, all delta I, and if you know all these coupling constants fi k, then you can compute everything else. So these objects are called, the collection of these numbers is called CFT data. And from here you can compute everything else. So to solve a conformal field theory, it means to find the CFT data. So in particular, you see this CFT data is defined from 2-point functions and 3-point functions. But in particular, knowing this, you can also compute the 4-point functions. So the 4-point functions are not independent. And we will have to discuss later on how to do this. So let's discuss the 4-point functions. Any questions about all this? Yes? Well, no, in QFT the 3-point functions are not zero. What is zero are the scattering, sometimes scattering matrices are going to be zero because you cannot satisfy on-shell conditions. But if you consider in a normal QFT 3-point functions of local operators, they are not zero. Well, theorem is inherent to free theories, to the Gaussian theories. So weak theorem in perturbative quantum field theory is useful because we are defining perturbative quantum field theory expanding around free theory. Here we are not going to expand around anything, so we will not have weak theorem at our disposal. There's going to be something else. So 4-point functions. I said that 4-point functions are going to be computable, but actually, to compute them, we will have to introduce a whole bunch of other techniques, which are going to be these dynamical concepts. And before we have done it, we can still ask, what does kinematics tell us about 4-point functions? Kinematics already tells us something. So these kinematical constraints of conformal invariance tell us that if you consider. So let me just consider one example, that if I take a 4-point function of 4 identical scalar operators, just for simplicity, then it can be written in the following form. So let me take this factor 1 over x12 to the power 2 delta. So delta is the dimension. And 1 over x34 to the power 2 delta. So this by itself would be conformally invariant, but that's not the only possibility. Actually, it turns out that here I can multiply this expression by any function f which depends on two parameters, u and v, which are called cross ratios. So this u and v are called cross ratios. And they have the following form. U is equal x 1 2 squared. No, let me write it. X 1. Yeah, x1 2 squared, x3 4 squared, divided by x1 3 squared, x2 4 squared, and v is equal the same as u, but you have to interchange points 2 and 4. So it means that v is equal, so the denominator is the same, x1 3 squared, x2 4 squared, but the numerator changes. It becomes x 2 3 squared, x1 4 squared. So the claim is that any function of this form is conformally invariant. So this is probably familiar from two-dimensional conformal field theory, and the same property is true also in dimensions larger than 2. Yeah, we can also do the same in 3D or in any number of dimensions, but let's discuss this. Yeah, let's discuss this. So before I discuss that, what do I want to say about so to discuss this I have to erase something. So let me. Any questions about this part of that I'm about to erase? No. Maybe before I erase, I'll write one more formula. So I'll first erase this. So here I had a case where all three operators were scalars, but suppose that this operator were a vector. So had an index mu. Again, a primary vector of dimension delta 3, but a vector. So in this case, the 3-point function will be of this form times an object which I will call R mu nu of x1, x2, and x3. And this R mu of, okay, I'm going to write an expression for x3 is equal to 0. So arc xy 0 is equal to absolute value of x, absolute value of y, divided by x minus y, times x mu over absolute value of x squared minus y mu divided by absolute value of y squared. So once again, it's fixed. And again, you can generalize it to more indices and so on. So actually, how do we check these formulas? How can you check these formulas? I said that all these formulas are conformally invariant. And it's clear that they are all invariant under translation, under rotation, and under scaling. But it's not clear that they're going to be invariant under special conformal transformations. So one way to check all these formulas would be to check that they are invariant under inversion. Because as we discussed last time, if you have inversion, then you can generate everything else. So you could, that would be one way to check these formulas, and that's what you could call a pedestrian approach. If you do things this way, this is going to look mysterious where all this comes about, because you would apply an inversion transformation, you see that things look not invariant, but then in the end there are some magic constellations and you acquire exactly the same expression. So I'm going to explain a different way to arrive at these formulas, which is much more direct and explains their origin a bit better. There was a question? Pedestrian, yeah, pedestrian. As opposed to driving a BMW. Okay, so then finally let's go back to this question about cross ratios. So all the formulas that I wrote them for general position of points, x1, x2, x3, x4. But it is possible, and it is in fact often convenient, to use the freedom of applying conformal transformations to move points around in order to set them to some convenient positions. Now, for example, the first thing you can do is you can try to apply inversion transformation to send one of the points to infinity. Now, once you set one point to infinity, you can now apply a combination of scaling and rotation to set one point to 0, to the origin, and one point distance 1 from the origin. Let me call it 1. So one point was sent to infinity. Let's call x4 going to infinity. And then this is x1 and this is x3. Just I chose it like this. So so we have one point left, x2. So it's somewhere in space. But now we can apply a rotation around this axis, which is going to put this point x2 in this plane, in the plane of the blackboard. So somewhere here there's a point x2. So this shows that for the 4-point function, actually for the 3-point function, if there's no x2, if there are only 3 points, this shows that there is no freedom, because we just set one point to infinity, one to 0, one to 1. If we know the value of the 3-point function at this configuration, we know the value of the 3-point function everywhere. So this explains why in conformal field theory 3-point functions are fixed. For the 4-point function, we have one point moving around, but what is the functional freedom? The functional freedom is, the coordinates of this point x2 in this plane. So there are two real variables, which are, the functional freedom is two real variables, or if you do two-dimensional CFT, you sometimes introduce a complex variable z. Two real variables or one complex variable z. So this functional freedom, two real variables or one complex variable, is exactly the same functional freedom that I see here. I expressed it in terms of two real cross ratios u and v, which can be expressed in terms of this z. Because you see, u is x4 went to infinity, so we can forget about this. x13 is 1, so u in this configuration is absolute value of z squared, and v is absolute value of 1 minus z squared. So it's exactly the same answering your question, it's exactly the same functional freedom that we have in two-dimensional CFT. So before we go to this BMW discussion, I want to make some remarks about how you can use this sort of results to check conformal invariance. So, as we discussed last time, there are some theoretical reasons to believe that the critical point of the 3D Ising model has conformal invariance. We also have very nice results for critical exponents which agree with everything else, and this tells us post factum that the assumption of conformal invariance these results are based on is consistent. But suppose you are a conservative person and you want to check explicitly by doing some sort of Monte Carlo simulation that indeed three-dimensional easy model is conformally invariant. How would you do this? Well, the most direct way to do this would be to measure on the lattice. So you do a Monte Carlo simulation and you measure on the lattice a 3-point function of some local operators. So you measure the 3-point function sigma epsilon epsilon in a Monte Carlo simulation, and then for various positions of points, and then you see whether the functional form that you get is consistent with the prediction of conformal invariance, with the formula that we've written. That would be one way to do this. Unfortunately, in practice, it's not easy, so this has not been done, because measuring 3-point functions on the lattice is not an easy task. So when you measure 2-point function, there is a certain amount of statistical noise, and if you go to 3-point function, then the statistical noise is much larger, and it's very difficult to get accurate results. So this has not been done yet. I don't know, maybe someone will come up with a method to do this. But there was a different, a related but slightly different way to do this test. And I wanted to say a few words about that. So this test is related to doing simulations. So normally when you do Monte Carlo simulations, you do them in some nice geometry, for example, periodic boundary conditions on some torus, right? Some slab geometry. But it turns out that it's interesting to consider Monte Carlo simulations for this question, not in the slab geometry, but in a geometry inside a ball. So you take a ball, say of radius 1, a three-dimensional ball. So you put here a lattice inside this ball. You only keep points which fit inside the ball with some lattice spacing A, and you throw out all the other points. And then you know what your critical temperature is, so you adjust your system to the critical temperature. And you now have a conformal field theory which lives not in infinite flat space, but it lives inside the ball. So it has boundary conditions. It turns out that conformal invariance gives you predictions. So if the theory is conformally invariant, then conformal invariance tells you also something about how the correlation functions behave inside the ball. So why is this so? Because you can apply a conformal transformation to map a ball to a half space. So I'm going to explain this, but conformal transformations map spheres to spheres. In particular, you can map a sphere to a sphere of infinite radius, which is a plane. And so you can map this to a half space. And using this trick, you can obtain some predictions about how correlation functions should depend on the positions of points. So let me write a few formulas here. So if here you have 2 points x1 and x2, then, for example, conformal invariance predicts that the 1-point function of an operator of scaling dimension delta inside the ball is going to behave like some constant divided by 1 minus x, so at the point x squared to the power delta to the power delta. So you see, we never discussed 1-point functions in full space, in flat space, because in 1-point functions in a CFT in flat space are 0 for dimensional reasons. Because if you have an operator of dimension delta, then a 1-point function in flat space would have to be equal to some mass scale to the power delta. And in conformal theory, since it's scale invariant, there are no mass scales. So it has to be equal to 0. But if you put the theory in a ball, then there is a length scale. There is a mass scale, which is the radius of the ball. So you can get 1-point functions. Analogously, you can also predict, and 1-point function should depend on x in this way, conformal invariance predicts. And analogously, if you take a 2-point function, or delta of x1 or delta of x2, then this has to be equal to 1 over 1 minus x1 squared to the power delta, 1 minus x2 squared to the power delta, times an arbitrary function, well, arbitrary, a certain function which is not easy to compute, but we know that it has to be a function, which should depend on a particular should depend on x1 minus x2 squared divided by 1 minus x1 squared, 1 minus x2 squared. So you see, here we had some arbitrary function of cross ratios, and here we also have some function of an object which you can also call a cross ratio, but for the ball geometry. And so why is this interesting? Because measuring 1-point functions and 2-point functions in the Monte Carlo simulation is much easier than measuring 3-point functions. And yet we have a non-trivial prediction for the functional dependence following from conformal invariance. And indeed, this has been done. So there was a Monte Carlo simulation. I can give you a reference. So some people did it last year. And they saw that these predictions are satisfied with good accuracy. Yes. No, scaling dimensions do not depend on R. Well, if if you don't set R to 1, then I have here R squared minus x squared. Yeah. Yes. Yeah. No, in half plane they are not 0. in half plane they are not zero. So in half plane, the 1-point function in half plane or delta of let's call this distance x perpendicular. Yes, something like that. Yeah, so it's going to be equal to, so x perpendicular, x parallel. It can be only equal to 1 over, well, some constant divided by x perpendicular to the power delta, because it's the only scale, x perpendicular. And now you take this, you map it on the ball, and you discover this formula. It's not really a global conformal transformation. Yes. Yeah. Well, a cylinder. Yes. Yeah, stress tensor is a special field in this sense. So I think this is a nice test which basically leaves no doubt that conformal invariance is there. Yeah. Yeah, I did not explain it yet. I'm sorry? No, of course not. I have not shown. Yeah. Before explaining that, I just mentioned this as an interlude. No, it's not a sphere, it's a ball. You really take three-dimensional space and you throw out all points. You keep only the points of x less than or equal to 1, and you throw out all the rest. Yes, you can do this mapping. But you do simulation, so you use this mapping only to derive this prediction. But when you do the actual Monte Carlo simulation, you just work on a finite lattice. But you so you take your Ising model and you just keep the spins which lie inside the sphere, and you throw out all the other spins. So it's an unusual Monte Carlo simulation. You don't impose periodic boundary conditions, so you just throw out those spins at all. Don't consider those links. You can impose. You have a choice whether to impose boundary conditions that on the boundary of the sphere all spins point up, or you may impose free boundary conditions. Okay. So let me explain these kinematic results. Where do they come from? So I already mentioned to you last time that actually conformal group in d dimensions is isomorphic to the group SO d plus 1, 1. Lorentz group in d plus 2 dimensional space. And so the idea is that we are going to build a formalism which is basically uses this Lorentz invariance in order to derive constraints from conformal invariance. So the challenge in finding such formalism basically is that conformal group acts on a space with d dimensions, while the Lorentz group acts on the space with d plus 2 dimensions. So we have to get rid of 2 dimensions, 2 extra dimensions somehow. But the advantage of this formalism is going to be that conformal group acts in particular a special conformal transformation, acts in some complicated nonlinear way, moves points around in some complicated nonlinear way, while the Lorentz transformation moves points around in a very simple linear way. So it's much easier to write objects which are invariant on the Lorentz group than to write objects which are invariant on the conformal group. So we were going to exploit this fact, and actually this whole idea is going back to the work of Dirac, I think, in 1930. So he already has foreseen this. So let me then introduce a D plus 2-dimensional space. So I'm going to call its coordinates large x1, large x2, and so on, xd, and then I have two more coordinates, xd plus 1, xd plus 2. So I'm going to call the first d coordinates x large mu, and I'm going to introduce so for these two coordinates I'm going to introduce their light cone combinations x plus minus, which are equal x d plus 2 plus or minus x d plus 1. So with these conventions, the metric, the Minkowski metric in this d plus 2-dimensional space is dx mu squared minus dx plus dx minus. So I'm not going to show this, but we are going to have the following identification between the generators of the Lorentz group and the generations of the rotation group. So with the Lorentz group, we have these generators, which I'm going to denote G mn, Jmn, where m and n run from 1 to d plus 2. And there's going to be the following identification, that G mu nu is going to be the same as M mu nu, and then G mu plus is going to be P, G mu minus is going to be K mu, and G plus minus is going to be equal to D. Actually, I'm not going to show this, and we won't even need these expressions, as you will see. The only reason I write it is that to show that there is enough space in this group, D plus 2-dimensional group, in order to fit all the generators of the conformal group. There's just enough space to do this. So now, Lorentz group has the fundamental representation. So Lorentz group acts naturally on a vector xm. It sends it into a matrix lambda mn xn. So it acts linearly. And as I said, the problem is that this representation is D plus 2-dimensional. Well, we need some action on the D-dimensional space. So we need to get rid of 2 dimensions. We need to restrict somehow this representation. And the first step, so we need to do 2 steps, and the first step is to go to the null cone. So let me consider the cone of null cone or light cone of points x squared is equal to 0. So the reason why I can consider it is that, of course, the condition x squared equals to 0 is preserved by the action of Lorentz group. So if I take a null vector, act with the Lorentz group, I get again a light vector. So I got rid of one. Now I have an action of the Lorentz group on the D plus 1-dimensional manifold. So I got rid of one coordinate. But that's not enough. I need to get rid of yet another coordinate, and for this I do this trick which is called projective. I go to the projective representation, which means I'm going to identify on my null cone all points which differ by a constant factor. So I'm going to identify points x with lambda x for any positive lambda. So here we go. So this again is a representation, and I got rid of one more coordinate. So I have a d-dimensional manifold on which my Lorentz group acts. So let me draw a picture. So this looks like this. I have this x plus, this x minus, I have here x mu. So this is my cone. And so if I take a ray, so my, the fact that I have a projective representation, it means that I consider the action not on points, but on rays. I have a ray. I apply a Lorentz transformation, and I map it to another ray. And the space of null rays is d-dimensional. So I have a d-dimensional representation. Okay, this may look a bit abstract, these null rays. If you are not very familiar with projective geometry, this may look complicated. But now I'm going to look at I'm going to make it very concrete. By giving the recipe how to recover from this action on null rays the action of the conformal group. So in order to do this, we are going to consider a section. So we are going to consider a section of my null cone. And the section is going to be given by the equation x plus is equal to a certain function, which I'm going to specify later, of x mu. So this section is going to be something like this. So it's a section. So if I specify x plus as a function of f, as a function of x mu, but of course x minus, then my null cone has equation x mu squared is equal to x plus x minus. This is the equation of the null cone. So if I gave x plus, then x minus is also given. So I know everything. And so my rule is the following. So don't worry, it's going to become very clear just in a second, if it's not clear where I'm heading. Actually, just to consider an example, the section that we are going to need in the end is x plus is equal to 1. That's going to be our section. Here I'm being general, but in the end I'm going to work with this section. So if x plus is equal to 1, it means that x minus is equal to x mu squared, right? So is equal to, so I'm going to write it like this: x squared and x mu is equal to x mu. So I'm going to write it like this. So in other words, I'm going to identify the big x mu with the small Euclidean x mu, then x minus is equal to x squared and x plus is equal to 1. So I put my Euclidean space inside this Lorentzian null cone. So this we are going to call Euclidean section. Euclidean section. And actually, it's not just a name, because Lorentzian space has a metric ds squared. So if you take any manifold inside the Lorentzian space, you induce on that manifold a metric from the Lorentzian metric, and you can ask, what is this induced metric? So let us compute the value of the induced metric on this Euclidean section. From dx mu squared you just get dx mu squared, but dx plus dx minus vanishes because x plus is a constant, is equal to 1. So on this Euclidean section I have ds squared is equal dx mu squared is equal ds squared. So the induced metric on this section is precisely the Euclidean metric that we need. So that's why it's called the Euclidean section. Right? And so now I have the recipe. Now I have the recipe to generate the action of the conformal group on the Euclidean section. So I start with the point here. I start with the point x. I consider a ray, a null ray which passes through this point. I apply a Lorentz transformation. I get another ray. I take the point of intersection of this other ray with my Euclidean section, and that's the action. This is the result. So I generated from the Lorentz group a transformation of the Euclidean space. Have I showed that this transformation is a conformal transformation? Have I proved this? Is it obvious that it's a conformal transformation? Sorry? Yes, isomorphism, suggests that it's probably a conformal transformation, but it does not prove it yet. So let's prove it. Let's prove it. It's not at all difficult. So the proof is the following. So let's consider here a small interval dx, right? And there's to show that the transformation is conformal, we must show. So we must show dx prime squared is equal to some constant factor times dx squared. Because this is the definition of transformation being conformal, that it changes the metric by a constant factor, right? So so when this point x, when we apply the Lorentz transformation lambda, we get here first this interval, let me call it lambda times dx. And for this interval, since lambda is a Lorentz transformation, so for this interval, this interval has precisely the same length as the initial interval. While what I'm doing here is just a rescaling of points along the direction. So let me write down it in equations. So I have the following equation: d lambda of x squared. So what I'm considering here is a rescaling. So I would like to know how the metric changes when I rescale with some factor lambda of x, which can depend on x. And so if I take this rescaling d lambda of x squared, then this is equal to, so let me just write down, so it's equal to dx plus x times d lambda squared. So if I now consider open the parentheses, then I get dx squared plus two more terms. One term which is proportional to x squared, so x squared d lambda squared, but this is just 0 because x squared is 0. We are on the light cone. And we have also the other term which is proportional to x dx d lambda. But this term is also 0 because since x squared is 0, when we differentiate, x dx is also 0. And so both of these terms vanish, and what I conclude that here, even though I rescale the metric by an x-dependent factor, in fact, sorry, here I had lambda dx, so here I have lambda squared. In fact, the variation of the factor doesn't matter. My metric is preserved up to a constant factor. Yes, exactly. Sorry. Yeah. So this is the yeah. So I skipped the first step because the first step preserves the metric. So the only non-trivial part is just to know what happens in the second step. Yeah. I think yes. Yeah. You are saying you are asking what's so special about this section, because I could tilt the things. So there is a projective representation, but to get from projective representation to the Euclidean representation, I have to pick a particular section. If I pick a different section, then I will generate conformal transformations. So conformal transformations can be defined on Euclidean space, or they can also be defined on a space endowed with an arbitrary metric. So if I tilt this section, then I will be dealing with conformal transformations not on the Euclidean space but on some other space. So this section is important. Any other questions? I think we should make a break, and I'll finish this story in the second part. I said, as usual, more things than necessary. So let me just repeat, because some of the things that I said were only serving as a motivation, others were instead operationally necessary. So let me repeat what is operationally necessary. I have this cone, x mu, x plus, x minus. In this cone, I have a section which I identify with my Euclidean space. And this section is given by the equations x plus, x minus, x mu is equal to 1, x squared, x mu. Now I want to define a conformal transformation on this space. The rule is the following. Take any point x, apply a Lorentz transformation in the d plus 2 dimensional space, so which is going to map me to some point lambda times x. Well, not x, lambda. So from this x, I'm going to go to x by this formula, right? And now I'm going to apply lambda times x. So far, so good. This is first step. Second step, since this transformation takes me out of this section, I have to apply a rescaling. Let me call it small lambda. So this point is going to be a rescale by an appropriate small lambda to get back into this section. So and this is going to give me a point x prime. That's all. So you can forget all the words I said about projective, so forget about it. It's just confusing, because this is just a recipe. First apply Lorentz, then rescale, period. Claim that this gives me a conformal transformation. In order to check that the transformation is conformal, I have to check that the metric, the metric from here to here transforms by a constant factor. I gave a proof of this. The proof was wrong. That was a kind of a trap. So I was waiting for you to point out. So as an exercise, give me a correct proof of this fact. It was not fully wrong, but it was a bit, there was some logical leap which was not justified. So, but the claim is correct. Yeah, this gives me a conformal transformation. Now, I want to use this in order to compute correlation functions of fields which are conformally invariant. correlation functions of fields, I had the rule for fields, how they transform on the conformal transformation. Now I have to extend these rules to fields which live not just on the Euclidean section, but on the full cone in order to use the Lorentz transformation. So let me give you the rule. The rule is going to be the following. So let's suppose I have a scalar field phi of x, which is a primary. It's defined on Euclidean space, and consequently is defined on the Euclidean section. Right? So I'm going to now extend this field to the full cone phi of x. I'm going to define phi of x by the following rules. So first of all, phi of x on the Euclidean section is, of course, going to be equal to phi of x. That's so far so good. This is the first rule. The second rule, phi of lambda x is going to be equal to lambda to the minus delta phi of x. So along the light ray, I extend my field homogeneously. So why these rules? Because I claim this is going to guarantee that the field phi of x transforms. Let me now give a third rule. This is also a third rule. So the third rule is going to tell me how this field phi of x transforms under Lorentz transformation. Well, this rule is very simple. So if I have a Lorentz transformation x prime equals lambda x, then of course phi of x prime is, so it's a scalar field, is equal phi of x. It just transforms scalar field as the way the scalar fields transform. Notice that this is of course for scalar fields, Lorentz invariant scalar fields. This is a good transformation rule. But for the conformal transformations, we had an analogous rule which had here a scale factor, right? You remember, there was a rule that phi of x prime was equal to omega to the power delta phi of x. That was the rule. And where is this going to come from? Well, it's going to come from here. Because you see, now if I take this rule and go through the two steps, so I start here, phi of x, I apply the transformation. According to the third rule, the field phi did not change. But now I have to rescale to get back to the Euclidean section. When I rescale, my field phi changes by the rescale factor to the power delta. And as I showed with the wrong proof, but you will give a correct proof, under this rescaling, the metric also changes by the factor lambda, by the same factor lambda. And so you are going to reproduce, starting from this rule, you are going to reproduce the rule that phi of x prime is equal to omega of x to the power minus delta phi of x, the usual rule that we had for primary scalars. It's going to follow. So I hope that at least intuitively this you should feel, at least you should get at least the intuitive feeling that this construction has a chance to work. So now you just have to carefully go through details, and this is done in my notes, by the way, the EPFL notes. Or you can do it yourself. So, any questions about the intuition? Yes.
The only part of the story that I'm intuitive about is this second line. So we're still operating in this large space of capital X.
Yes.
We have lambda times x, so we're going down this way.
Yeah.
How does the delta enter here?
How does the delta enter?
Where does it come from? I wouldn't know. I mean, I'm still in this Lorentz space with this delta.
no, what I'm defining here, so my conformal field theory will have a primary field of dimension delta. Now I have to define an object on the Lorentzian cone which corresponds to my primary field of dimension delta. So I'm telling that I'm going to define it as a field which scales along the cone, which is homogeneous along the cone, and the homogeneity factor is lambda to the delta. So each primary field which will have its own homogeneity factor. So this is completely up to us. This is arbitrary, just like it was arbitrary in the conformal group case. This just defines delta. Yeah, it just defines delta. What I really mean by this equation is that in the end, the way I'm going to interpret this equation is the correlation functions at the point of fields at the point x prime are going to be equal to the correlation functions at the point x. Right? So this is how you should interpret this equation. You can call it phi prime or phi. The correlation functions are going to be equal. But okay, so once again, this may look a bit confusing, but now there's going to be a clarification point. Now everything is going to become absolutely clear, because I will give you concrete rules how to apply this formalism, and in a sense you will see that these rules are so simple that you can apply the rules even if you don't understand fully this derivation. So it's going to be very nice. So let's just start with the 2-point function. So I want to derive, so I gave you this, so we know that the 2-point function of a primary scalar is equal to 1 over x minus y to the power 2 delta. So let's derive this very simple result in this language. So in this language, I'm going to study a correlation function of phi, but in terms of these big variables, x and y. And in order for the final answer to be conformally invariant, the answer written in terms of x and y should be Lorentz invariant. So it should be a function, and now Lorentz invariance, we know what Lorentz invariance means. It should be a function of x squared, y squared, or x times y. But x squared and y squared are equal to 0, because we live on the null cone. So x squared and y squared cannot enter. The only thing which can enter is x times y. So it's going to be equal to 1 over x times y to some power. But what is this power? So I told you that that the field phi has to scale homogeneously. If I change x by lambda x, it has to rescale by lambda to the minus delta. So we have to insist that this equation be consistent with this scaling property. And by the way, this scaling property should be true for independent rescalings of x and y. So it's clear that it's going to be true if and only if this power is equal to delta. Right. No, delta. Because, I rescale x by lambda, and here it's lambda to the power delta. And y, I rescale y, I also get y to the power delta. So this is the form of the two-point function on the cone. Okay, good, but we are not really interested in the two-point function on the cone. We would like to go back to the Euclidean space. Well, what should we do? We should now substitute x equals 1 x squared x mu, and y is equal 1 y squared y mu into this formula. We should go back to the Euclidean section. Right, so let's do this. So x times y is equal x mu y mu minus 1/2 x plus y minus plus x minus y plus. Scalar product. So we substitute and we get x times y minus 1/2 x squared minus 1/2 y squared. So we get minus 1/2 x minus y squared. So on the Euclidean section, this scalar product x times y is nothing but the Euclidean distance squared between the points up to this prefactor, which is not important because we can always scale it away. And so we reproduce this formula. Where's this formula? Sounds good. We reproduce this formula, but now we can immediately reproduce all the other formulas that I've written. Let's just go through the list. Suppose these two fields have two different scaling dimensions. I told you that in this case the two-point function is 0. Well, how do we see this? Well, because we would have again 1 over x times y to some power, but this power, I said that we should be allowed to rescale independently x and y. And so you see that you can, whichever power you choose, either the rescaling property of x or rescaling property of y is not going to be satisfied. And so you cannot write anything with the required rescaling properties. So in this case, the two-point function is 0. Let's go to the three-point function. So phi 1 x1, phi 2 x2, phi 3 x3. So this is going to be equal to 1 over x1, x2 to some power alpha, x1, x3 to some power beta, x2, x3 to some power gamma. This is just Lorentz. But now I have to impose scaling. So if I rescale x1, I have to get lambda to the power delta 1. So it means that alpha plus beta has to be equal to delta 1. And analogously, alpha plus gamma has to be equal to delta 2. And the beta plus gamma has to be equal to delta 3. So we have three equations on three unknowns. We solve them. We get the same numbers that I gave you, this h, a, g, k. You go back to the Euclidean section. Each one of these scalar products, x1, x2, becomes the Euclidean distance squared. And so we reproduce the formula that I've written before. And so now when you go to the four-point function level, there the only there were these cross ratios which I said were conformally invariant. So if you write these cross ratios, well, let's write u, for example. U was equal to x1 times x2 x. So now I'm writing what is this cross ratio on the cone? X1 times x2, x3 times x4, x1. No, sorry, it was differently. No, it's fine. X1, x4, x2, x3. No, x1, x3, x2, x4. So if you go back to the clear section, you acquire the expressions that I was writing before. So I claim that this is conformally invariant. So why is this conformally invariant? Because it's, if I rescale any of these coordinates independently, x1 or x2 and x3, there is no scaling. It's since x1 enters both in the numerator and denominator, it scales with weight 0. And so such a quantity is going to give rise, when projected to the Euclidean section, to something which is completely invariant under conformal transformations. And so this proves the formula for the 4-point function that I've written. So here's my exercise then. So using this formalism, derive a formula for 4-point function O1, O2, 4 scalars, O3, O4, for different dimensions. I only gave you the formula where all 4 dimensions were identical, but now that you know this general principle, you should be able to write a formula for 4 different dimensions. So what remains to be said here? I only presented you the projective null cone formalism for scalars, but of course it can be generalized also for fields with indices. This requires a few extra ingredients, but not much. So about this you can read in my lecture notes. And you can use this to derive the formulas that I was writing in the first part of my lecture. So I think that's it. I think we can consider that kinematics is under control. So our conformal kinematics is under control. Any questions? Yeah, so the question is what conformal invariance tells us about Lorentzian CFTs. So this is this is an interesting question. So it applies not just to CFTs but to any quantum field theory. So suppose you solved quantum field theory in Euclidean signature. What can you say about the same quantum field theory in Minkowski signature? And well, in this case, you have to perform the weak notation, perform some analytic continuation, and there a problem with the sound? Maybe the battery is dying or something. Yeah. No?
Probably is a failure in the cable.
Maybe the cable.
Yeah. So maybe you don't touch too much the cable.
Yeah, I'll try not to. Yeah. Yeah, I'll try not to touch the cable. So in some cases, this analytic continuation is really trivial. Like for example, for the 2-point function, you have 1 over x squared to the power delta in Euclidean space, and you just, when you rotate to Minkowski, this just becomes Minkowski x squared. And then you, depending on the ordering, you have to put an I epsilon prescription. So then it's really simple. For 3-point functions, it's also the same. And for 4-point functions, it's more complicated. So because this I epsilon prescription, this analytic continuation, becomes more subtle when you go to higher point functions. It still remains true that you can obtain Minkowski correlators by analytically continuing Euclidean correlators, and they will have more or less the same functional form, but you may acquire some extra pieces from crossing various singularities in the complex plane. Okay, so then we can move on to our next subject, which is unitarity. So we'll discuss unitarity, and then we'll go to dynamics later on. So this is an extra constraint. So we discussed the constraints of conformal kinematics, and now there's going to be some more constraints, more axioms, if you wish, that we also need to take into account. So unitarity is the first one. So what can I say about unitarity? So I presume that we are all familiar with unitarity in quantum mechanics. So in quantum mechanics, we just have, Hermitian Hamiltonian, and we have a Hilbert space, which is positive definite. In this case, we can construct a unitary evolution matrix, and so we have unitarity. This is familiar. Now, if you do quantum field theory, then if you do quantum field theory, the usual quantum field theory in Minkowski space, then, for example, if you do canonical quantization, this is just to set the stage. Then it's the same. So if you do say equal time canonical quantization, then again we have a Hamiltonian, we have Hilbert space. So again we have unitarity. But here we are doing not this, but at least the way I set up things, we are doing Euclidean quantum field theory. And so, natural question: what plays the role of unitarity in Euclidean quantum field theory when we don't have time, strictly speaking, we just have correlation functions and like in the three-dimensional Ising model. And so here, the role of unitarity is played by a property which is called reflection positivity. Can I have a show of hands? How many people familiar with reflection positivity? Okay, good. So it means that my job is going to be not in vain. I'm going to increase. So the way it works is the following. Let me first define reflection positivity. I take my Euclidean space, say RD, and I pick one coordinate out of d coordinates arbitrarily. It's completely arbitrary. For example, I pick x1, pick x1. And so I define my reflection transformation theta, which takes the point x, which is x1 xd, and it maps it to theta x, which is minus x1 x2 xd. So it's just a mirror transformation with respect to the first coordinate. So this is on coordinates, and now I also define the action of this theta on fields. So I say that theta acting on the field phi at the point x is the field phi at the point theta x. And then I have the following property, that if I have a correlation function in which I have a bunch of fields, phi of x1, phi of x2, and the same fields with theta applied, theta phi of x1, phi of x2, dot dot dot, so which means that these fields are in fact inserted at the reflected points, right? The way I write them. So such a correlation function. So here I have n fields, and here I also have n fields. So it's a 2n correlation function, even number of fields. So such a correlation function is always non-negative. So this is the definition of reflection positivity. So I have a plane x1 equal to 0, and I insert a bunch of points above the plane and the same number of points below the plane at precisely mirror positions, and this has to be always non-negative. So this is for scalars, and there is a natural extension of this concept to vector fields. So if I have a vector field, then I define this reflection operator acting on the vector field by multiplying. So I have a mu nu at theta x, and then multiply it by -1 to the number of times I have an x1 index. So n1 is the number of x1 indices. Which is natural. So if you have a vector field which is points parallelly to the reflecting surface, to the reflecting plane, then there is no minus sign. If I have a vector which points perpendicularly when I reflect, then of course I multiply it by -1. And the same property remains true for this definition. So this is just a definition, but why is this an interesting definition? Well, because there's a theorem, first of all, for several reasons. So first of all, there's a theorem which is a classic result, from the glorious days of early quantum field theory by Osterwalder and Schrader, who proved, well, it must be 60s or 70s, I don't know when, in the old days, that if you have a Lorentz invariant QFT in Minkowski, this is equivalent to have a weak rotated, sorry, Lorentz invariant unitary QFT in Minkowski. This is equivalent to having a weak rotated reflection positive QFT in Euclidean. So reflection positivity is really the Euclidean space analog of unitarity. And while this theorem, okay, if you want to prove it at the mathematical level of rigor, it's maybe not so easy. Well, it is not so easy, but to get an idea, to get an intuition why this is the case, is not so hard. So let me show this, and then we'll make a break. So the idea is that so let's take a Minkowski theory, and let's take in Minkowski theory an operator, a Hermitian operator, phi. So then its dependence on time is given by the Heisenberg picture relation, phi of 0 e to the minus IHT. In particular, you know, if you take this expression and if you conjugate it, phi t dagger, then you get back phi of t, if the operator is Hermitian. But this was in the Lorentz, so this is in the Lorentz in the Minkowski space. But now, if you go to the Euclidean space, so if you want to define a Euclidean operator, which depends on the Euclidean time, then this is defined as the Minkowski operator at the time minus IT Euclidean. This is the weak rotation. So if you plug this in, then you get e to the HT Euclidean, phi of 0, e to the minus HT Euclidean. And so if you now take a conjugation, then, you know, before you had a complex exponential. Now you have a real exponential. So you see that if you take a conjugation, then these two terms get interchanged, and you get phi Euclidean of minus TE. So you see, it's a weird feature, well, weird if you're not familiar, of working in the Euclidean with weak rotated fields, is that the conjugation actually flips the sign of Euclidean time. So when I consider a correlation function of with fields which are inserted at times, by the way, x here of course is just goes for a ride. There's nothing changes. When I consider a correlation function, when I have here a bunch of fields inserted at some positive times, Euclidean positive times, and the same fields inserted at negative Euclidean times, then these fields are Hermitian conjugates of the other fields. And so the whole correlation function can thus be interpreted as a norm of a certain state, because it's something times something dagger. And, you know, if our theory was in the Minkowski space with which we started was unitary, then the norms are positive, and so this correlation function has to be positive. So here we go. I proved that under weak rotation you get reflection positive Euclidean field theory. That's not the most ideal place to stop, but still I have to stop here. Yeah. There is a relation. That was what I was about to discuss next, but I will have to do it my next lecture. I'm sorry? There is 15 minutes? No, because there has to be a break before the next lecture, unless you want to say that my lecture is so captivating that you don't want to have a break. It's okay. It's okay. Let's make a break.